Now we've had a look at how to find the resultant vector, we need to also know how to resolve vectors. Okay, and this comes from a very basic principle, and that principle is that vectors at right angles, vectors which are orthogonal, vectors which are normal, vectors which are at right angles, do not affect each other. Okay, so these forces, force 1 and force 2, will not affect each other. You can push something forwards as much as you like, it will never turn left or right, as long as you're on a Euclidean plane. Anyway, basically, if you can push something forward as much as you like, it won't turn left or right. That hopefully should intuitively make sense, right? If you have a gun, okay, and that fires a bullet horizontally, and at the same time you drop a bullet, okay, so you just let go of a bullet and you fire a bullet horizontally, as long as you drop them from the same height, they will hit the ground at the same time. Although this bullet here has a huge force going to the right, it doesn't matter in terms of their vertical trajectory because they both have the same acceleration down, which of course is g. Okay? Forces which work at right angles do not affect one another, which is why it is so useful when we have a force or a vector going at an odd angle to be able to resolve it into its two right angled components. Okay, so let's take an example here. We've got our force moving at an angle. I want to put that to a vertical and a horizontal component because it will become useful later when we're trying to add them up. So the way we do this is we draw out our force at the angle, and we can draw along here a horizontal component and our vertical component. Now, this is kind of like shining a light down onto it. Okay, so if we shine a light downwards, you can see that this will map on here. Okay, and if we shine a light to the side, this our force, our initial force, will map to the left. Okay, so we've essentially broken up our one force into two kind of shadow forces, if you like, two shadow vectors, which have the same height and the same width, respectively. Okay, so we've got our force at the angle and we have our two shadow forces. We can again look at Pythagoras to try and resolve this. This whole process is known as resolving a force, taking a force at an angle and putting it into its horizontal and vertical components. So we can draw our triangle. You can see there, again, I've moved the vectors, but I've kept the magnitude and the direction the same. So it is essentially the same vector, so I'm allowed to do it. Okay? So we've got the same angle there, we've got the force there. Now, because we can use SOHCAHTOA, because it is a right-angled triangle, because the whole point of this is we are resolving them into two right-angled vectors, we can find out the two forces, right? So we're going to call this our vertical force and our horizontal force. So that's our horizontal force and our vertical force. So vertical, we have our hypotenuse, so we know we're not going to need tan, and it is the opposite length to the angle. So we're looking at sine. So sine of theta equals the opposite, which is v over f. So we know that v equals f sine theta. Let's do this again, but for the horizontal component. We've got our hypotenuse, so it's not tan, and we're looking at the adjacent length to the angle. So we know it's going to be cos. So cos theta equals our adjacent angle, which is h, over hypotenuse, which is f. So we know that h equals f cos theta. So we can write, therefore, we can map this vector into our two shadow vectors, our horizontal, which we know is f cos theta, and our vertical, which is f sine theta. And this whole process is known as resolving a force.